We have already discussed the generation of double sideband suppressed carrier, like the modulation methods, different modulation methods like ring modulator, single balanced modulators. Now in this lecture we are going to discuss the detection of the double sideband suppressed carrier modulation detection or demodulation. The very first method which is going to be preferred for the detection, so that is known as a synchronous detection. So synchronous detection is nothing that is the band pass filter. So that is the balanced modulator follows low pass filter. So that is the synchronous detection method. So the input of the balanced modulator, so that is the block diagram of the synchronous detection. The input of the balanced modulator is double sideband suppressed carrier. So that is the product of the message signal and the carrier signal. So for the synchronous detection, we have to locally generate the carrier signal which is very well synchronized with the oscillator that was used at the transmission side or during the generation of the double sideband suppressed carrier. So the synchronous should be very perfect, like, so that is why it is known as the synchronous. And the output of the balanced modulator is xt. So xt is basically the product of the double sideband suppressed carrier and the carrier signal. So that is mt cos omega ct multiplied by ac cos omega ct. So that is cos square t. So we already know that cos square is equals to 1 plus cos 2 theta divided by 2. So we can rewrite this formula in this case like AC by 2 mt 1 plus cos 2 omega ct. We can open that. So AC mt plus AC by 2 mt cos 2 omega c. So we know the frequency of this is Fm and the frequency of this is 2 Fc plus minus Fn. So if we draw the spectrum of that signal, so spectrum is looks like this one. So this is the spectrum of that message, and you know the low pass filter. So that is low pass filter. So it means that the Fm can easily pass through the low pass filter whose tuned or center frequency is Fm. So this will pass. So this will pass from that low pass filter. So the spectrum of that second is 2Fc is centered frequency and 2Fc minus m and 2Fc plus m. So it will low pass filter will block this signal. And the output of the low pass filter is Yt. So Yt will be equals to AC by 2 mt. So it means that this is a perfect recovery of the message. But like here, as I said, we have to use the synchronized local oscillator or the carrier signal. So the local oscillator frequency should be frequency and phase should be synchronized with that carrier signal. So let's suppose if your carrier signal is not perfectly synchronized, that one what happens? So we will take two cases. Case one is that the effect of phase drift, like if the phase is not perfectly synchronized, so the local generation, like the this signal, we can write that signal AC cos omega ct with certain phase drift. So and then we can again write the value of xt. Xt is the product of this and the double sideband suppressed carrier. So this is the double sideband suppressed carrier, double sideband, and this one is the locally generated carrier signal, so with certain phase. So this can be written in this format. So AC by 2 mt, and then it is the trigonometric function cos AB, cos like 2 cos the 2 cos A cos B equals to cos A plus B and then plus cos A minus B. We can use this formula here. So cos A plus B and then cos A minus B. So this is cancel out. So this one will be cancelled out, and this is this one and 2 mega ct plus theta, and then the remaining is cos theta. So the frequency of this is 2 Fc and the frequency of that is Fm. So it means that when you multiply this with that one, then the frequency is FM. So the low pass filter will block this message, and you can have that message at the output AC by 2 mt cos theta. So if theta, like you can say theta is varying, but if theta is 0, then it is fine. So but as we said, it is a drift. So in that case, if theta is 90, then cos 90 is 0, and then your message will be 0, like you did not recover anything. So this effect you can call quadrature null effect. Why quadrature? Because cos omega ct plus 90 is equal to sine. So sine is the quadrature component of the cos. So that is why name is quadrature. Why null? Because we are getting 0 output, so that is why the name is null. So the name of this effect is quadrature null effect. The second case is the frequency drift. So like if your locally generated signal has a certain drift of the frequency, change in the frequency. So this is the frequency drift, omega c plus delta omega, and then your xt is the product of the double sideband suppressed carrier and this signal. So again you can use that formula cos AB and cos A cos B is equals to cos A plus B plus cos A minus B. So if you use this, so this is equals to 2 omega ct plus delta omega plus cos delta omega. So you know this frequency of that is fc 2fc plus minus fm. So that is why it will not allow to pass this one. Only that is the output of the low pass filter, mt by 2 cos delta omega. So since the you know the amplitude of the cos is continuously changing, so it will change the amplitude of the message signal as well. So it means that you will get distorted signal at the output. So this effect is known as beat effect, like you are not recovering the signal. So what are the conditions if you want to perfectly recover the signal? That your locally generated signal should be very well synchronized with the frequency and the phase of the oscillator that was used at the transmission side. So that's I'm going to end my lecture here. So I hope that you have understood very well the synchronous detection of single double sideband suppressed carrier. If you still have any question, you can write your question in the comment box and we will try our best to answer the question. Thank you for watching the video.